All right, let us start. Yeah, the last two questions are relatively hard. Because you missed a lot. Yeah. First, question number 9. The answer is 5. 5 more comparisons, you can get it sorted. 4 not enough. You have to do 5 comparisons. Let me show you how to do 5 comparisons. Let me just draw a diagram. We already know x1, x2, x3 in that order. Let me just draw in that way. x1, x2, x3. Yeah. Then we need to put x4 and x5 in place. All right? So let us try one by one. Yeah. x4, when we insert x4, we compare it with x2. Binary search idea. Binary search idea. Okay? So you only have 2 possibilities. x4 less than x2 and x4 greater than x2. Only 2 cases. But these 2 cases are symmetric, right? One up, one down, just mirror flip, up becomes down, down becomes up, right? Yeah. So you only need to consider one case. One of 2 cases, because the other one's symmetric. You don't need to consider twice. Okay? Symmetric, one is enough. All right? Yeah. The second case, just you flip, mirror flip, you get second case. All right. So let us assume we only consider one case. That is this one, x1, x2, x4, right? Yeah. x4 less than x2. Here. x2, x3. Now, x5. We still compare it with x2. Okay? Yeah. Still compare it with x2. Then you have 2 cases. x5 less than x2 and x5 greater than x2. 2 cases, right? Yeah. So let me draw 2 cases somewhere else. Yeah, I hope I have enough space. Yeah. All right, let me draw smaller. Yeah. x1, x4, x5, 3 smaller than x2, x3. That's one. Another one, x1, x4, x2, x3, x5. Right? These 2 cases. Remember, we did 2 comparisons. When we get these 2 cases, we did 2 comparisons. So let me draw comparison 1, comparison 2. Okay? All right. For this case, we just need 2 more to get sorted. All right? Yeah. x1, x4. So comparison number 3, x3, x5, comparison number 4. Only 2 more comparisons, total 4 comparisons to get sorted. But this is not the worst case. We need to work for the worst case. This is the worst case. All right. For this case, we need to get the top 3 elements sorted. Right? 3 elements, top 3 sorted. 3 more comparisons. Right? Yeah. Because to get top 3 sort 3-element array, you need 3 more comparisons. So now the total 3 plus 2 equals 5. Worst case, 5 comparisons. So this one is relatively hard. Relatively hard. Yeah. When you do comparison, always compare the one in the middle, binary search way. Binary search way. Yeah. So then the remaining cases, not too many, only 2 cases. 2 cases. One is worst. Yeah. So that's question number 9. The last one, most of you did partially correct. Yeah. Partially correct. Yeah. All right. So we know, yeah, x1 less than x2 less than x3, b1 less than b2 less than b3 less than b4 less than b5. All right. And x2 greater than b3. All right. A element, A positions, the median is this one, 4th. Okay? 4th. Yeah. Now, look at that. When you try to eliminate the elements that cannot be the median, you need to look at from 2 ends. Yeah. Some students only look at from one side. Then you miss a lot of information. Here we look at from 2 sides. Okay? Yeah. All right. Elimination. Here we do the elimination. Okay. First, look at x3. x3. x3 greater than x2, and x2 greater, yeah, look at how many elements x3 greater than. b1, b2, b3, and a2, and a1, right? So x3 greater than at least 5 elements. So x3 should be eliminated. Yeah. Yeah. So x3 greater than 5 elements. Yeah. All right. Then let's just look at x2. Oh, sorry. Yeah. 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 All right. x2 greater than 4 elements, right? b1, 2, 3, and a1, but the median can only greater than 3 elements, not 4. So x2 greater than at least 4 elements. So a2 can be eliminated. No. a1 not. Okay? a1 we don't have information, so a1 we cannot eliminate. All right. Then the other side, oh, yeah, here, yeah, just still left-hand side, b5 greater than at least 4 elements. Okay, yeah, b5 at least 4 elements. So b5 can be eliminated. All right, yeah. All right, so that's from the left-hand side. From the right-hand side, yeah, b1 less than 4 here, and 2 more from A subarray, A array. b1 through b3 less than a2, a3. So b1 less than at least 6 elements. Yeah, at least 6 elements. So b1 can be eliminated. Okay, yeah. Then b2 less than 3 in the B array, and a 2 in A array, at least 5 elements, right? At least 5 elements. So B2 can also be eliminated. All right, B2, all right? Yeah. And the B3 less than 2 elements in B array, 2 elements in A array, 4, but not enough to exclude it from the median consideration. We only find 4 elements for sure greater than B3, but A1 we don't know. A1, it's possible greater or less than B3. We don't know, unknown. So B3 cannot be eliminated. Then you can see the answer. The elements that can be eliminated, A2, A3, B5, yeah, let's count from. So B1, B2, B5, and the B4 greater than 3, but we don't know what else it can be greater than, right? Yeah, A1 we don't know. Okay, yeah, even A1, A2, we cannot say B4 greater than any of them, right? Yeah, so B4, it's possible to be the median. So eliminated. So this is the eliminated. Yeah, eliminated. Considered. A1, B3, B4. Okay? Yeah. So you should be very careful from 2 sides. Yeah. Yeah. Most of you just missed 1 or 2. Yeah. Got a lot, but still missed 1 or 2. Yeah. All right, so that's the midterm, all the questions, and I will post my annotated, and also the video. Yeah, after the class, I convert the video. Video conversion very slow. Last time I didn't finish, so when I went home, I couldn't recover it. Anyway, but this time I tried to make sure I get that for you, so you don't, because you go through all the questions. I just post this PDF. When you see this file, you know what's going on. But 3 students who missed this class, they need to look at the video. When they see things like that, they may not be able to understand the details. All right. So that's this part. We put it behind. Next, I prepare examples. Yeah. So I have one topic, remaining topic for hashing left. Let me leave it next time I complete that part. So this time I talk about examples. Give you a few, do review for final. Yeah, this time I do review for final. So the remaining hashing part, I feel I may need about 40 minutes. I complete the hashing. Then I just do the review for final. Okay? All right. Yeah. So in part A, I make 6 questions. Yeah. Today we may not be able to complete it. I just go a little slow. Yeah. So part A, I put 6 questions. Part B also 6 questions. Total 12 questions. Relatively hard questions. So let me explain the details. So in our final, we have Part B, relatively hard questions based on these questions. Okay? Yeah. So I give you these examples. Yeah. Then I modify a little bit. So then you can work on Part B of the final. Yeah. All right, so let's start. Yeah, so let me test the PowerPoint. All right, yeah. Question 1, 2, 3, 4, 5. Yeah. All right, so the first question. Let me use this way to write things well in this way. Yeah. All right. And change my pen color. All right, let's start. Given a max heap with 500 nodes whose position number correspond to 1 through 500. Now we consider a particular node with position 123. What is the height of this node? Yes. All right. Let me draw array with position number 1 through 500. All right. Then, regarding the height, first, let us review the height formula. Height formula. Yeah. So we get that formula. Okay. We derive the formula level height h nodes. Yeah, height h nodes. Yeah. So let me review that. All right, so first, leaf nodes. Leaf nodes, we know height h equals 0. That's the leaf nodes. Okay? And our formula for leaf nodes remember that. Range. Last one. Position number n. First one. N over 2. Floor function plus 1. Remember that. That is the leaf node. This range is for height h. Height h equal to 0. Okay? All right, so let us look at the, this point. Let us calculate n over 2. N equal to 500. Okay? N over 2 floor function plus 1 equal to 251. All right, so this point, 251. Okay. So this range, height equal to 0. Okay? Yeah. Height equal to 0. All right. Then height equal to 1. Height equal to 1. Okay? Then 2 point, upper bound, n over 2, lower bound, n over 4 seeding function plus 1. Okay, this is the range. Upper bound, height 1, 250. Lower bound, 500 over 4 floor function plus 1. 125 plus 1, 126. Okay? So 126. This is for h equal to 1. Okay? Based on our formula, this range for h equal to 1 by that range. Okay? That calculation. Okay. Below, after that, 123, you can see not in this range, 123, position number 123. Okay, yeah, not in, oh sorry, not, yeah, 123, not in height 1 range, here. 125 lower bound should be 500 over 8 plus 1. Yeah. What's that? 508. So 6, 2, right? 62 plus 1, 63. Okay? Yeah. So this lower bound, 63. Yeah. So 123, that corresponds to this range, h equals 2. Okay? Yeah. H0 range, H1 range, H2 range. See? Yeah. So the answer is 2. Okay? Answer is 2. Yeah. So this question mainly check if you know these formulas. That formula. Remember the general formula, height h range. Yeah. Height height h range. Okay, yeah. Lower bound, upper bound. Okay, yeah. Upper, yeah. Upper bound. Right? Upper bound is this. Lower bound, how about that? That is height 8 range, height h range. This general formula. Okay? Yeah. Yeah. So if you know this one, many questions can height h. Yeah. Corresponds to high h nodes. All right. This question. Next one. Given a heap with 42 nodes, how many leaves are there who have the longest path from the root? Yeah. Longest path from root. All right. You need to recover the binary tree. Yeah. We know 2 to the k minus 1 less than or equal to 42. Because we want to see the complete binary tree part before the last bottom level. Bottom level. Okay? So we do this calculation and we see k equal to 5. Yeah. That is 32 minus 1 less than equal to 42. Okay? Yeah. All right. So for the binary tree, if we draw okay, yeah, binary tree, okay, complete binary tree. Here, 31 nodes. All right, 42 minus 31 equals 11. That means there are 11 nodes at the bottom level. Nodes, okay, at the bottom level. Then, the longest path from the root, we should start from the root and reach one of the 11 bottom level leaf nodes, one of the 11, yeah? So you know the answer. That's the longest. That's the longest, not those leaves. Those leaves not the longest, okay? These leaves, one less than the longest. So you can see the answer is 11. 11, okay? Yeah. So the calculation, we do like that, okay? Binary tree, yeah. You need to draw that binary tree. Yeah. Then look at the bottom leaf level. How many? Yeah. Subtraction, yeah. That will tell you the number of leaves at the bottom level. At the lowest level. That's second question. Yeah. The third one, this one, given an array with elements, only 4 elements, how many different max heaps can we build from this array? You need to draw all the possible max heap with these 4 elements, 4 numbers. Yeah. The number we use the max heap because there is you know, the parent value. The parent value should be greater or equal to any of the child value, right? Yeah. The parent value must be greater, yeah, or than or equal. So we need to draw all possible max heaps. All right? Yeah. The first thing is easy, right? 4 must be at the root, right? 4 must be at the root. Largest value should be at the root. Yeah. That is the first thing we can determine. Then left subtree, left child, right child. Think about that. Yeah. Heap structure should be like this, right? Yeah. Heap structure, near complete binary tree. That's near complete binary tree, right? Near complete binary tree must be in this way. You cannot do, you know, for example, you put this here. No, that's not here. Here you have to arrange in order, okay? In order, like that. The question is how to fill in these 3 numbers, 1, 2, 3, in it. How many possibilities? Okay, yeah. All right, 3. 3 cannot be here, right? 3 cannot be, because this number should be less than its parent number. 3 largest in the remaining 3 numbers, so 3 cannot be there. All right, it's only 1 or 2. Okay, 2 cases, 1 or 2. Okay, yeah. So let's put a 1 case. When 1 is here, 1 is here, then two here, 3 here, 2 here. How about that? 2 cases. Yeah. When 1 is here, you can put a 2 there, 3, or 3 there, 2. Yeah. 2, 3, or 3, 2. All legal, right? Yeah. 2, 3, 3, 2. So in that case, this case you have 2. All right. Then another possibility. Because you can also put a 2 there, right? If you put 2, 1 must be there, 3 must be here, right? Yeah. Because you cannot put a 1 there. The parent number should be greater or equal to the child number. So only 1 possibility, right? Yeah. So this case, you only have 1. 1, 2 plus 1, 3. So the answer is 3. The answer is 3. See? That's how we determine the max heaps, all possible max heaps. You need to be familiar with the structure of max heap. Yeah. So that is the reason I can let you do this type of questions, because only 4 elements. Not too many. If too many, you know, nobody can do it. Too many possibilities. Yeah. 5 possible. Yeah. 5 not too hard. Yeah. But a question. Yeah.
So why is the left like binary thing equal to 2, but the second one is equal to 1?
All right. Yeah. Let me go back. Okay. First, you know the structure must be like this, right? All right. All right. The first thing, 3 cannot be here, right? 3, because if 3, what is the number in its parent node? Parent value must be greater or equal to, so 3 largest. 3 cannot be here. Then you only 2 possibilities, 1 and 2. All right. That's why you consider 1, then consider 2. Yeah. When you fix 1, all right, so that's why 2 or 3, 3 or 2, 2 possibilities. Yeah. So the remaining, yeah. Good. Yeah. Just ask question. Okay. Yeah. In this way, you can understand. Yeah. Because you have a good possibility, I may give you a question 1, 2, 3, 4, 5. All right. Yeah. 1, 2, 3, 4, 5. All the possible heaps. If you don't understand, you cannot solve it. 1, 2, 3, 4, 5. 5 must be at the root. Other than that, you know, branches. Yeah. 1, 2, 3, 4, 5. First, we can draw that binary tree structure first. Okay. 5 is here. Then, look at that. The structure is like that. You need to fill in 4 numbers. Look at that. Okay. 4 numbers, the possibilities. Okay? Yeah. Probably I plan to give you in the final. Yeah. So I don't mind give you at this point. Okay? Yeah. Okay? Yeah. All right. Next one. Given a max heap whose values corresponds to the array index from 1 to n. What is the smallest possible index for the second smallest value of the heap? Yeah, this one. Still, we need to understand the structure of a max heap well. Yeah, this one, let me show you. Yeah, because based on my experience before, the students miss this question a lot. Yeah, so let me solve this one here. Smallest possible index for second smallest. All right? Smallest possible. Remember, we have a range thing, right? We have a range thing. The second smallest element only less than the smallest. Only greater than the smallest. Yeah. That means it can only have one leaf. One leaf child, only one. So now you want to see which internal, yeah. Because in order to have, all right. Let me draw that diagram another time. Remember, in our question 1, I draw this diagram. So let me draw that diagram, part of it, another time to answer this question. Okay. And this block corresponds to leaves, right? Leaves. Okay? Yeah. Leaves occupy this block. Okay? And we know leaves with height 0. Okay? Yeah. All right. Now, second smallest, we want to find the smallest possible index for second smallest. Push that to the, we want to push second smallest to the leftmost position. Leftmost possible position, we can place that second smallest element. Okay, push to its, but we cannot push too far to the left. Otherwise, it won't be the second smallest. That's the point. So we just want to find the position that could be used to put the second smallest. That's it. Could be. Yeah. There is a possibility to put second smallest there. That's it. Okay? All right. All right. First question. Do you want to consider second smallest one of the leaves? You don't, right? Because you can still push it to the left. Okay? Yeah. First, second smallest could be anyone in the leaf. It's okay. So that means this one. But you want to go further to the left. Yeah. So it can have at least one child, right? But not two. It can have at least one child, but not two. If it has two children, it cannot be second smallest, right? Yeah. So here, we find a critical property. Critical property for the second smallest element. Okay. It can only have at the most one child. Okay? Yeah, one child. Okay? All right. Then the answer is this one. The one with position number, this only one to its left. Okay. Oh, just a minute. This could have two child, right? Just a minute. That is a possible, right? Possibility. Yeah. Based on even odd. Okay? Yeah. All right. Yeah. So the answer when n is even. When n is even, remember, yeah, if we consider n over 2 as the one, n here, but no position to the right, right? Because out of bound. When n is even, we only have one child here, but no n plus 1 there, all right? Yeah, so that is okay. Okay, but when n is odd, yeah, so here, n is odd, here n minus 1 over 2, right? Because the floor function equals n minus 1 over 2. Okay? N minus 1 over 2, then 2 leaves, right? Here, n minus 1, here, and how about that? When n is odd, that floor function corresponds to this number, so it has 2 children. Okay? All right. So the answer for this question, you know, answer when n is even, it is n over 2. Okay? Yeah. When n is odd, it cannot be this one, okay? It can only be that one. It cannot be this one, yeah, because two children, okay? So the leftmost position for second smallest is this one. So that is, it is n plus 1 over 2. N plus 1 over 2. Okay? Yeah. See? So this question helps you understand structure furthermore. Okay? Yeah. At the most, one child. If 2 children, it cannot be second smallest. One child, at the most one child. Okay? Could be 0 child, it's okay. 0 child, so no violation. Yeah. All right. All right, yes. Now, this question. Question number 5. When we merge 4 sorted array with 10, 15, 12, 37, respectively, what is the minimum number of comparison for the best case? Best case, yeah, here. First, let's recall the best case formula to merge two ordered arrays. The first array with m elements. Second array with n elements. The best case minimum of m and n. Okay? Minimum of these two numbers. All right. Yeah. Now, we have four ordered arrays. Four ordered arrays. Okay. One with 10 elements. The second one with 15 elements. The third one with 22 elements. The last one with 37 elements. Because when we do the merge, there are many possibilities, right? There are many possibilities. The question is, how do you want to do the combinations? There are so many possibilities. How do you want to combine? Okay? All right. So here, to show, here, let's say A. Let us use number of elements A, B, C, D with A less than B less than C less than D. Okay? Yeah. All right. Let us look at, let us try out two examples, two random examples, and see if we can get something useful. Okay. All right. All right. For example, let us merge A and B first. All right? Yeah. C and D second. Let us merge this way. Okay? Merge A and B, we will get number of comparison. A comparison, but with A plus B elements, right? Yeah. So here I need these two numbers. Number of comparison, number of elements, the meaning. Yeah. This side, number of comparisons. This side, number of elements. Okay? Similarly, for C and D, after the merge, we get C comparison, but the C plus D elements. Yeah. All right. Then we merge. After that, we need to merge A plus B subarray and a C plus D subarray, and number of comparison A plus B, number of elements A plus B plus C plus D elements. All right. So now total number of comparisons equals A plus C plus A plus B, okay, equals 2A plus B plus C, okay? Yeah. So in this way, 2A plus B plus C. Okay. Yeah. All right. I may like to try another way, and we compare if we can get a smaller or bigger than this one. Try another way. Okay? Yeah. 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 So this one, ABCD is hard, yeah, but yeah, probably, yeah. Yeah. So let me use the space. Yeah, I have a little space, yeah, because I do not want to use a different page. Let me use the small space here to do another example. Okay. All right. Yeah. AC and BD. How about that? Yeah. AC and BD. AC and BD, we will get A comparison with A plus C elements. BD merge, we will get B comparison with B plus D elements. All right. Then we merge A plus C and a B plus D with A plus C comparison. Yeah, so that oh, all right. With minimum A plus C comparison and A plus B plus C plus D elements. Yeah. Total number of comparisons. Total. A plus B plus A plus C. The same, right? Yeah. Look at it. In this way, we get the same answer. 2A plus B plus C. Okay? Yeah. Yeah. So here you can see probably this should be the answer. Yeah. You can try if you can get smaller, so probably not. Yeah. All right. Yeah. Yeah. But here, yeah. The thing is, we need to show. Yeah. We need to see. Yeah. Here the question. Yeah. Yeah. Here I leave the question here. Okay. Yeah. Let me use this small space. Question. How to find the best solution. Although you try possible cases and pick the one with the smallest number comparison, you can do it in that way, because these four numbers, the number of cases, not too many, we can handle. Yeah. But the question, can we prove rigorously, or can we find an argument that can tell us the best solution formula quickly? Yeah. So that probably hard. Yeah. That probably hard. Yeah. All right. Yeah. I will think about that. Okay. I will think about that and see how hard it is. If it's too hard, so then I won't give that question to you. Okay. If I feel not too hard, so we can handle, so then I tell you that solution. Yeah. Then there is a possibility you may have that question. Okay? If the solution for this question is not too hard, too messy, what I mean hard or easy, not too messy. If it's too messy, then I don't want to give it to you. Okay? Yeah. If not too messy, very neat, then I will give it to you. So then there is a possibility you may have this kind of question in the final. Okay?